Today, let's take a look at the second law of thermodynamics and the associated content of entropy. Entropy, which is related to randomness or disorder of the system. It's very important to bring in this concept of entropy because there are a lot of processes which for example, mixing of gases or things coming in equilibrium, temperature, when two different temperature blocks are brought together. Many more examples are there where there's absolutely no energy change, delta U or delta H. Either of them is zero, both of them is zero. Uh, so, what should be the driving force over here? How do I know that a reaction or a process is spontaneous? Huh? And that's where the concept of entropy comes in use, and we'll take a look at that. Okay. Now, entropy is something that we wish that it should be a state function. It should depend on the state. And what I'll go to do is to see this. And randomness, as we've seen already, has been associated with heat. But heat, if you see, delta Q reversible is given by du minus delta W reversible, the first law. And we know du is Cv dt for an ideal gas, and delta W happens to be PdV minus PdV, so it's plus PdV. And for an ideal gas, Cv dt plus nRT by V dV. So we could write it that way. But we know that delta Q reversible or irreversible happens to be a path function. Not because of this particular term, this is definitely integrable. But here we have uh, the variable V, volume, but also we have the variable T, which indirectly depends on the volume. And as you've seen already in case of isothermal and adiabatic processes, the temperature is not the same. So it really depends on the path that is being followed. So I need to know the path in order to be able to get the integral value of this person. I do not want a path dependence if I need a state function. So the easiest thing that I can think of over here is to divide everything by temperature. If I divide everything by temperature, the first term has only temperature, can be integrated, and the second term has only volume, again it can be integrated. So delta Q reversible by T is something that you define as entropy of the system. ds is equal to delta Q reversible by T, and now it's a state function. Now 1 by T happens to be the integrating factor because this allows you to integrate the entire expression. Also, if you think about this, if I am at a low temperature, then increasing the temperature creates disorder. Yes? But if you think of it, changing the temperature when I am at a low temperature, so lower temperature over here means the disorder is much more. Yeah, come to think of it, a, a material at a high temperature is already disordered, so I can increase the temperature slightly, and the amount of disorder or randomness would not change so much. But if I am at a very low few kelvins, then the amount of disorder would change drastically. So T is something that also speaks of the disorder and relates ds to disorder. Okay. So the heat absorbed at given temperature. Now, although I've defined it to be a state function, let's take the case of the expansions that we've taken earlier, isothermal and adiabatic plus isochoric expansions. If I, again, I'll consider an ideal gas. If I look at the isothermal expansion going from point A to point B, then I know delta Q reversible is minus of delta W reversible. Du is 0, of course, for an isothermal case for an ideal gas. So it comes out to be delta Q reversible in the isothermal case comes out to be nRT1 by V dV, or integrating it, Q reversible comes out to be nRT1 log V2 by V1. In the adiabatic case, there's no exchange of heat, reversible or irreversible, whatever it is. So it comes out to be 0, right? And for the isochoric case, delta Q is equal to du, which comes out to be Cv times dt. So the total thing, Q reversible from A to C and C to B, added up together is T2 to T1, right? Cv dt. We can integrate this because this is du, I know, and Q is nothing but the change in internal energy going from C to B, so I can do that integration. And we've seen in the last lecture, we've seen over here, right? So from the last lecture, I've seen Cv by T dt is equal to minus R by V dV. So I can use that. T1 to T2 Cv by T dt is equal to minus V1 to V2 nR by V dV, which comes out to be minus nR log V2 by V1. So using this expression, I can know what my T2 is. How to relate this? I could use this expression straight. So going from V1 to V2, I know what is the change. Although this is not for the adiabatic process, but still I can use this expression and get to know my T2. Right. So we've seen Q is Cv into T1 minus T2, and Q over here is nRT1 log V2 by V1. It is different for both the paths. But what about delta S, which is integral of delta Q reversible by T? And let us see delta S. It's easy to calculate for this. Since T1 is a constant, I could just divide it and get nR log V2 by V1. And for the adiabatic plus isochoric case, for the adiabatic, I know delta Q is 0, so anyway delta S, the entropy change, is also 0. For the isochoric case, delta S is T2 to T1 integrated Cv by T dt, right? So this divided by T dt. And we've already seen from the last lecture, I could straight away use the result nR log V2 by V1. Look at the two yellow expressions, they're exactly identical. So the entropy change on going from A to B is nR log V2 by V1, whichever path you take. So entropy definitely is a state function, as we see in this particular example. It's independent of the path, whereas the heat was independent of the path. So this particular state function, which describes randomness, is independent of the path. Okay. Now, coming towards the second law, in the sense of Clausius inequality, what Clausius says is something very easy to understand, that the first law is given by du is equal to delta Q. So the total internal energy is nothing but the heat exchange plus the work done. Whether it's done irreversibly or it's done reversibly, du comes out to be the same. So I can rearrange this expression. I could say delta Q reversible minus delta Q is equal to delta W minus delta W reversible. Okay? And this is always greater than 0. Always. Why? Because if you think of an expansion work, then delta W is negative, and the maximum work is done when it is reversible. So the highest negative value would be when it's reversible. This would be a lower negative value. So in total, this would be a positive value. If you think of compression, then the work that is done on the gas is positive, and it's the minimal amount of work that you can do to compress when you do it reversibly. So this would be the lowest positive number in case of compression. This would be a higher positive number in case of compression. And the difference would always be greater than zero. So delta W minus delta W reversible in either case happens to be greater than zero. Therefore, delta Q reversible minus delta Q is always greater than or equal to 0, or delta Q reversible is always greater than or equal to delta Q, and I can divide both sides by T, the temperature. So delta Q reversible by T is always greater than or equal to delta Q by T, and we know that this fellow is nothing but ds. So ds is always greater than or equal to delta Q by T, right? And this is true for an isolated system. Yes, we are talking of one system. This is true for an isolated system. ds is greater than or equal to 0, because for an isolated system, delta Q, I will not be able to exchange any heat with anything, yeah, since it's isolated. So once it's isolated, then ds is greater than or equal to 0. And if you think of the universe, then it's an isolated system. Okay. So the entropy of the universe is always increasing, right? And if you think of an isolated system, some reaction that is going on or some process that is going on, once the reaction comes to an equilibrium, there's no further change. And in that case, when there is no further change, so I can think of the entropy that keeps on increasing and then flattens out to 0, because then the change in entropy, the entropy keeps on increasing and flattens out to a constant number. The change in entropy does not occur anymore when you reach equilibrium. So ds is 0 at equilibrium. And if you think of a reversible process in an isolated system, then remember, the reversible process is always maintaining an equilibrium. Huh? When we had a reversible expansion of gas, then the pressure external was equal to the internal pressure, and it was always at equilibrium. I could reverse it at any time. So whenever it's an isolated system at equilibrium, then again we know that the change in entropy is 0. Okay. For other systems which are not isolated, how would one calculate this entropy? How would one get to know the entropy? One has two parts of the system. One is the system itself. Okay, let me not call it two parts of the system. Okay, two parts of the whole arrangement, let's say. One is the system, and the other is called the surrounding. Hmm? For a spontaneous process, ds system plus ds surrounding must be greater than or equal to 0. Right? So that's what the second law is. The second law says that the entropy of the universe is always increasing. Hmm? Entropy of the universe cannot decrease for a spontaneous process. Okay, let's take a look at some of the examples, and then you'll see that the entropy really does increase. And it goes along with what you would call as common sense. Huh? Think of two metal blocks, one at temperature T1, the other one at temperature T2. Initially, these two temperatures are not equal, and then we connect these two blocks. Hmm. The moment we connect these two blocks, what happens? From everyday knowledge, we know that the temperature of both the blocks would come to some equilibrium temperature, would be somewhere in between T1 and T2. Okay, so let us take a look at this particular system in terms of entropy changes. And remember, this system is an isolated system. So this thick black line outside tells you that this is disconnected from the outside world. the change in entropy would be the change in entropy of the first block plus the change in entropy of the second block, which is the heat exchanged by the first block by temperature of the first block plus heat exchanged by the second block divided by temperature of the second block. And I know that whatever heat is given by block 2 is taken up by block 1 or the other way around. So delta Q1 is equal to minus of delta Q2, and I can replace that over here. So what it gives me is delta Q1 into T2 minus T1 divided by T2 T1. Now, what we have seen is that the change in entropy is greater than 0. Yes, for a spontaneous process. So if this ds is to be greater than 0, then delta Q1 T2 minus T1, this is of course the denominator is greater than 0. So delta Q1 into T2 minus T1 should be greater than 0. If T2 is greater than T1, then delta Q1 should be a positive number, which means if block 2 is at a higher temperature, heat should flow into block 1. That's common sense. If block 2 is at a lower temperature, then heat should flow out of block 1 to block 2. Yeah. Positive heat means heat flows in, negative heat means heat flows out, right? So this does support the idea of ds being greater than 0 for spontaneous change. Okay, let's take a look at another example, an isothermal expansion. Now, if I look at an isothermal expansion, I'm going from, let's say, volume V1 to volume V2, state 1 to state 2. So the delta S for the system comes out to be, we've seen above over here, nR log V2 by V1 for the isothermal case. Yeah. So delta S of the system comes out to be nR log V2 by V1. Whether it's a reversible or an irreversible process, it doesn't matter. I know entropy is a state function. Okay. If I have an irreversible process, all I need to do is to think of a reversible process. And usually what you would do is, if I'm going from 1 to 2, go back from 2 to 1 in a reversible manner, calculate the entropy change. Okay. And once you've calculated, take the negative of that. Okay. So now this is a reversible process. I know delta S for the system is nR log V2 by V1. What is the heat exchanged with the surrounding? Whatever the heat is given by the system or taken up by the system, the negative of that. So minus of dq. Always that is the case. Now for a reversible process, delta S surrounding would be Q surrounding by T, which is minus of Q reversible by T. Right? Q reversible is the heat exchanged in the reversible process. And I know minus of Q reversible by T is minus of nR log V2 by V1, because I know Q reversible by T is nR log V2 by V1. So the total change in entropy, it's a reversible process, so it should be 0. It does come out to be 0. For an isolated system, for a reversible process, it should be 0. Remember that, yes. Now, it's an isolated process when I consider both the system and the surrounding. That makes the complete universe, and that is isolated, right? But if I think of free isothermal expansion, free means against an external pressure of 0, against vacuum. Isothermal, so delta U is 0. Free, so pressure is 0, so work done is 0. Naturally, the heat exchanged is also 0 as per the first law. So delta S surrounding is also 0. The total entropy change is delta S system plus delta S surrounding, which is nothing but delta S system nr log V2 by V1. And since we are talking of an expansion, V2 is greater than V1, so this entire expression is greater than 0. Remember, this free expansion is an irreversible process. It's a spontaneous process. It's a sudden thing that happens against vacuum. When you do reversibly, you're holding the pressure constant. Not constant, you're holding the pressure in equilibrium with the, so the external pressure is in equilibrium with the pressure of the gas. But here you have a constant zero pressure. It's an irreversible process. So again, delta S is greater than 0. One more example, mixing of two ideal gases. Think of bromine and nitrogen at ordinary temperatures. They don't react with each other. The change in entropy over here can be written as nr log V2 by V1 or minus nr log V1 by V2. Right? So bromine, once I open this throttle over here, then whatever the volume, do not worry about the volume of this connector. We could even bring them closer, have zero connector. So let's say these are two volumes. So the volume of bromine gas, bromine goes from this container into this container, and nitrogen goes from here to here. And finally we have a mixture of bromine and nitrogen which is homogeneous throughout. So bromine now has both these volumes available. Nitrogen also has both these volumes available. So V2 is the combined volume. So minus number of moles of nitrogen times R log V1 by V2. And the change in entropy for bromine is also the same. Okay, this is an isolated system. Remember that. Okay. So if I look at the total change in entropy, then it's delta S N2 plus delta S bromine. I just add up the two terms. And I also know that the volume is proportional to the number of moles in case of an ideal gas. So instead of volume, I can write number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of bromine over here. Likewise in the second expression. Okay, and then I can define the mole fraction yi is equal to number of moles of species I by total number of moles. So this term would be y of N2 and this term would be y of bromine, like we have log of yn2 log of y bromine. And then I also divide the entire expression by n total. So this also becomes y of N2 and this becomes y of bromine. And delta S divided by the total number of moles comes out to be delta S mixing per mole divided by gas constant R is equal to minus y n2 log y n2 minus y br2 log br by br2. Y happens to be a mole fraction, so it's always less than 1. Log of that would be a negative number, so negative times negative is all positive. So delta S mixing is greater than 0. There is no temperature change, there is no energy change, only the gas is mixed because the delta S mixing is positive. The randomness increases for these gases.